we shall continue with the second PUC portions. Okay, so the first topic under second PUC portions probability is conditional probability. So the first topic under the second year probability syllabus is conditional probability. So what is conditional probability? In the first year, we have studied about probability of an event. So every event, for every event, there is a number associated, okay, that we call it as probability of that particular event. But what is conditional probability? Conditional probability is one step further. Can we think of finding out the probability of one event with respect to another event or not? So that idea is called conditional probability. So to define what conditional probability is, we need a minimum of two events, okay, pertaining to the same sample space. So please make a note of that. We should not be taking two events connected to different sample spaces, but we have to take two events connected to the same sample space of a particular random experiment. Okay, so the definition of conditional probability goes like this. Two events E and F be associated with sample space capital S. Two events E and F, two events capital E and capital F be associated with the sample space capital S. Then conditional probability of event E with respect to event F, we can think about that. Okay, conditional probability, like I told you, we are going to find out the probability of one event with respect to another event associated with the same sample space. So we have taken two events, events E and F of the sample space capital S. We are going to think about probability of event E with respect to event F. So that is called conditional probability of event E with respect to event F. The notation for conditional probability of event E with respect to event F is written like this: capital P of E bar F. Okay, so this is the notation for conditional probability of event E with respect to event F. So this is read as P of E bar F. Okay, in other words, conditional probability also means that what is the probability of event E given that event F has already occurred. So you just remember this point also, because while solving the problems under conditional probability, this idea is important. So another meaning of conditional probability is probability of event E given that event F has already occurred. So coming back to the definition, what is conditional probability of event E with respect to event F? It is nothing but equal to probability of the event E and F. So the notation for probability of event E and F is this: P of E intersection F whole divided by P of F. P of F is nothing but probability of the event F. Okay, there is one particular condition here. As you can see that this is a ratio of probabilities of events E and F and the event F. So the denominator cannot be 0, right? So in mathematics, division by 0 is not defined. Hence you have to write the condition P of F not equal to 0. So I repeat the definition once again. To think about conditional probability, you need a minimum of two events associated with some sample space S. We have taken two events E and F, associated with the same sample space, capital letter S. Okay, so conditional probability of event E with respect to event F, or in other words, probability of event E given that event F has already occurred, notation is P of E bar F. It is nothing but equal to probability of event E intersection F whole divided by probability of event F. The only thing is that we have to note that probability of F cannot be 0. If at all probability of F is equal to 0, then P of E bar F has no meaning. So you cannot define conditional probability of event E with respect to event F if at all probability of event F will be equal to 0. Okay, can we think about conditional probability of event F with respect to event E? Definitely. So the notation just changes to P of F bar E. Instead of P of E bar F, which is the notation for probability of E with respect to F, we write probability of event F with respect to E. Okay, so what is this equal to? Same way, in the place of E we put F, in the place of F we put E. So it is P of F intersection E whole divided by P of E. So P of F intersection E can be written as P of E intersection F itself divided by P of E. Why is this so? Because sets F intersection E and E intersection F are one and the same. Okay, so in this expression, what exception are we going to make? The denominator, correct. P of E should not be equal to 0. In this case, P of F should not be equal to 0. Since P of E is in the denominator here, we have to write the condition P of E cannot be equal to 0. Okay. This is about conditional probability. When we are solving problems based on conditional probability, the concept will become much more clear, but for now this is sufficient. Okay, moving on, the next topic is properties of conditional probability. Properties of conditional probability. There are 3 properties in total. Okay, we will start like this. Let us consider a sample space S and let A, B, E and F be events of sample space S. I repeat once again. We have taken a sample space S. A, B, E and F are events of sample space S. One more condition is that probability of event F will not be equal to 0. So we'll make this restriction P of F, probability of event F is not equal to 0. So this applies for all 3 properties. Let us look at the first property. So the first property states that P of S bar F equals P of F bar F equals 1. So the first property is telling us P of S bar F, which is nothing but conditional probability of the sample space with respect to event F is equal to 1. Also P of F bar F, conditional probability of event F with respect to itself is also equal to 1. So the proof is very simple. We'll first show that P of S bar F is equal to 1. We'll consider P of S bar F. Okay, so look here, by definition of conditional probability, how can we write this as? Okay, we saw what P of E bar F is equal to. So what is that equal to? P of E bar F is nothing but P of E intersection F by P of F. Okay, similarly in the place of E we have S here. So what happens to the formula? It becomes P of S intersection F divided by P of F. Okay, so all I have done is I have used the definition to write down the formula for P of S bar F. Now, what is sample space? S is sample space. F is an event of S. So F is a subset of set S. F is subset of set S. So what will S intersection F be? It will be nothing but P of F. Since, why is this so? S intersection F is nothing but equal to F. F is a subset of S, hence common elements between sample space and set F will be nothing but elements in set F. So this becomes P of F whole divided by P of F as it is. These two cancels and we get it as 1. So we have proved that P of S bar F equals 1. Further, we have to show that P of F bar F is also equal to 1. So that is extremely simple. Again, we use the definition. So what is P of F bar F? By definition of conditional probability, it is P of F intersection F whole divided by, I can write it as P of F. So P of F intersection F divided by P of F. But what is P of F intersection F? It is nothing but P of F whole divided by P of F. These two cancels and again you get back 1. So we have proved that P of S bar F equals 1 as well as P of F bar F. Okay. Moving on to the second property. These conditions apply for all three properties. So the second property is like this. Property number 2. P of A union B bar F equals P of A bar F plus P of B bar F minus P of A intersection B bar F. So this is property number 2. A, B, E and F are events of sample space S. One more condition we have, probability of F not equal to 0. Then this result is true. What is this result? P of A union B bar F equals P of A bar F plus P of B bar F minus P of A intersection B bar F. One more special case of this result is that if A and B are mutually exclusive events, then this result becomes P of A union B bar F equals P of A bar F plus P of B bar F. So the third term we will not write because the third term will be 0. Okay, whenever A and B are mutually exclusive events, this property number 2 reduces to this expression. P of A union B bar F is equal to P of A bar F plus P of B bar F. The third term will not be here. Okay, we will first prove property number 2, and thereafter when A and B are mutually exclusive, we are going to derive this property from this property. Okay. So this is the special case. First we will prove property number 2. Okay, look here. We will start off with the LHS and then prove the RHS. We will consider, this is the proof, we consider the LHS. What is the LHS? LHS is P of A union B bar F. LHS is P of A union B bar F. Now, we will use the definition of conditional probability. What do we know about the definition? We know that P of E bar F is nothing but equal to P of E intersection F by P of F, right? So by definition, we know that P of E bar F is equal to P of E intersection F divided by P of F. But look at this. What is there in the place of E? We have A union B. So the only difference is in the place of E, we have A union B. In the place of F, we have F. So by definition of conditional probability, what happens to this? We have P of A union B intersection F whole divided by P of F, right? So we have used the definition of conditional probability and we have written the formula for P of A union B bar F, which is nothing but P of A union B intersection F whole divided by P of F. Then, using the properties of the distributive property of union and intersection of sets, what happens to A union B intersection F? What do we know about A union B intersection F? We know that distributive law holds good for under sets for union and intersection. So what happens to this? We have A intersection F union B intersection F. So I can write that as A intersection F union B intersection F. So I substitute that here. I get P of A intersection F union B intersection F whole divided by P of F. So you have got P of A intersection F union B intersection F whole divided by P of F. Now we can just recall the first PUC result, okay, P of E union F. So how can we write this as? I can write this as P of E plus P of F minus P of E intersection F. Okay, just recall this result, students. We have P of E union F is equal to P of E plus P of F minus P of E intersection F. Look at this numerator. Okay, let in the place of E we just have A intersection F. So in the place of E we have A intersection F, and in the place of F I have B intersection F. So A intersection F I can consider it as one event. B intersection F I can consider it as one event. So using this formula, how can we write the numerator as? I can write it as P of E. E is A intersection F. So P of A intersection F plus P of F. What is F here? I can consider B intersection F as set F. So that is P of B intersection F. What is the last term? Minus P of E intersection F. So minus P of E. In the place of E I have A intersection F. In the place of F we have B intersection F. So what will that become? P of A intersection F intersection B intersection F. So we use the first PUC result, P of E union F equals P of E plus P of F minus P of E intersection F to write the numerator. So whole divided by P of F as it is. I hope there is no confusion here. If there is confusion, just pause the video, look it up, and then continue watching the video. Okay, we'll move on further. I'll just rub this. Okay. Now look at this last term, P of A intersection F intersection B intersection F. How can I write this as? So we have A intersection F intersection B intersection F. Okay, I can write this as A intersection F intersection B intersection F. This follows from associative law of intersection of sets. Okay, I have removed the brackets and I have used brackets for F intersection B. Okay, is intersection of two sets commutative? Yes. So F intersection B, I can write it as B intersection F. So I will write this as A intersection of F intersection B. I will write it as B intersection F intersection F. Okay, this follows from intersection of sets being commutative. Then again we will use the associative law of intersection of sets. I can associate A intersection B intersection F intersection F. Okay, A intersection B we perform first, intersection F intersection F we are performing again. That is by associative property of intersection of sets. Okay, now how can I write that as A intersection B intersection F intersection F is nothing but set F. So F intersection F is nothing but set F. So what is A intersection F intersection B intersection F? I can write it as A intersection B intersection F. So what happens to this last term? So these two terms I write as it is, P of A intersection F plus P of B intersection F minus, so in the place of A intersection F intersection B intersection F, I can write this. So this becomes P of of A intersection B intersection F whole divided by P of F as it is. Okay, moving on further, I can split the terms. Okay, I will write the first term as P of A intersection F by P of F, then plus P of B intersection F by P of F, and the last term I can write it as minus, because there is a minus sign here, P of A intersection B intersection F whole divided by P of F. So we have written the next step. We have split the terms in the numerator and we have just separated and written the terms. Okay, now again look at the definition of conditional probability. What is this expression P of A intersection F by P of F? I can write it as conditional probability of event A with respect to event F, right? So how can I write that as P of A bar F? So this is nothing but P of A bar F. Similarly, look at this. What is this? By definition of conditional probability, correct, it will be P of B bar F. Again, look at the last term. We have P of A intersection B intersection F divided by P of F. It is nothing but minus P of A intersection B bar F. So we have arrived at the RHS. We started from the LHS, we used certain properties, definition of conditional properties, certain first PUC probability results, and we arrived at the RHS. Okay. Now all there is left to do is to prove that the third term P of A intersection B bar F is equal to 0 whenever A and B are mutually exclusive. So we'll do that now. So property number 2 we have already proved. We need to prove the special case of property number 2, right? When A and B are mutually exclusive events, then property number 2 reduces to this result. P of A union B bar F equals P of A bar F plus P of B bar F. The only difference between these two is that the third term is missing. Okay, in fact the third term value will be equal to 0. So we are going to actually prove that the third term value is 0, hence making this expression, reducing this expression to this equation. Okay, all we have to do is we have to prove that P of A intersection B bar F is equal to 0 whenever A and B are mutually exclusive events. Okay, we'll consider this P of A intersection B bar F. Okay, so by definition of conditional probability, what is P of A intersection B bar F? It is nothing but P of A intersection B bar intersection F whole divided by P of F. This follows from the definition of conditional probability. P of A intersection B bar F is nothing but P of A intersection B intersection F whole divided by P of F. Okay, now what kind of events are A and B? A and B are mutually exclusive events. So when A and B are mutually exclusive events, what can you say about the set A intersection B? It will be nothing but the empty set or the impossible event. So substituting this idea here, what happens to the numerator? We have P of A intersection B is the empty set, intersection F whole divided by P of F. Okay, further, empty set intersection F is nothing but again the empty set, because there are no common elements between the empty set and set F. Hence this becomes P of the empty set, that is probability of empty set divided by probability of event F. But we all know that probability of the empty set is 0. Since P of F, we already said that it is not equal to 0, the value of this expression is 0. So P of A intersection B bar F is 0 whenever A and B are mutually exclusive events. So what happens to this property number 2? If P of A bar intersection B bar F, if this is 0, okay, all there is remaining is this P of A union B bar F equals P of A bar F plus P of B bar F. So the third term has reduced to 0. Okay, moving on. The last property this is the third property. Okay, this states that P of E dash bar F is equal to 1 minus P of E bar F. Okay, so A, B, E and F are events of sample space S and P of F not equal to 0. Then P of E dash bar F. What is the event E dash? It is nothing but the event not E, right? It is the complementary event of event E. So we have to prove that conditional probability of event E dash with respect to F is nothing but 1 minus conditional probability of event E with respect to F. Again, we will start with the LHS and prove the RHS. For the proof, we will use the first as well as the second properties. Both properties we are going to use here. We are supposed to consider property number 1. We'll consider property number 1, P of S bar F equals 1. Okay, so I am using property number 1 to prove this statement, property number 3. Property number 1, we know it to be P of S bar F is equal to 1. Now, can I write S as E union E dash? Of course. Why? Because event E is a subset of sample space S. Hence, we can write sample space S as equal to union of events E and complementary event of event E. So union of these two events will be nothing but the whole sample space S. So this result reduces to P of, in the place of S, I will write E union E dash. So that is E union E dash bar F equals 1. I repeat once again. So the third property is P of E dash bar F, that is equal to 1 minus P of E bar F. We need to prove. We have taken property number 1. What is property number 1? P of S bar F equals 1. This we know and we have just now proved. But what else do we know? E is a event. It is an event of sample space S, meaning it is a subset of the sample space S. What is event E dash? It is the complementary event of event E. So is union of these two events the whole sample space S? Yes, it is also true. So S equals E union E dash. What I have done is P of, in the place of S, we have written E union E dash bar F equals 1. Now, moving forward, it is also true that E and E dash are mutually exclusive, events. So by the definition of complementary event, E and complementary event of E must be mutually exclusive events. By property number 2, special case of property number 2, what do we know? If A and B are mutually exclusive events, then P of A union B. So we are using property number 2 here. P of A union B bar F is nothing but P of A bar F plus P of B bar F, right? So whenever A and B are mutually exclusive events, then P of A union B bar F is equal to P of A bar F plus P of B bar F. But what are the events here? We have the events, instead of A union B, we have E union E dash. Okay, so what happens to this LHS? This becomes P of E bar F plus P of E dash bar F equals 1. So the LHS becomes P of E bar F plus P of E dash bar F. RHS remains as it is, equals 1. So just taking this term that side, we take the term P of E bar F to the RHS. What happens to this expression? We are left with P of E dash bar F equals 1 minus P of E bar F, which is nothing but the statement of property number 3. So I explain this once again. P of E union E dash bar F is equal to 1. Okay, we have used property number 2, special case. P of A union B bar F equals P of A bar F plus P of B bar F. In the place of A we have E, the place of B we have E dash. So this LHS becomes P of E bar F plus P of E dash bar F equals 1. So taking this term to the RHS, we have P of E dash bar F equals 1 minus P of E bar F. So we have proved property number 3. So these are about properties of conditional probability. These have not been asked in the final examination till now, but you just remember these, okay? The result and the proofs you just remember, but remember that, also remember that these properties have not been asked in examinations till now. Problems based on conditional probability we shall solve in the next class. Thank you.